Hey everyone, this is a slightly different video than my usual ones. It's actually mirroring a blog post about a beginner's introduction to transformer models that I put on my website a couple days ago. This video is a bit of an experiment where I took my blog post, which is 100% written by me, a human by the way, and plugged it into an AI agent that I built that has generated the entire script and visuals that follow in this video. So apologies in advance for putting more AI slop on the internet, but it is a fun experiment and you should definitely check out the blog post in the description because it's a lot more detailed, and I know I'm biased, but I think it's pretty well written. But yeah, be mindful of any visual or script quirks. It's a bit of a work in progress, but yeah, enjoy.
Transformers are the backbone of some of the most groundbreaking AI breakthroughs in recent years. From ChatGPT to GPT-4 to Claude, these models power the AI tools we use every day. But how do they actually work? Let's demystify the magic behind these powerful language models. To understand transformers, we need to start with neural networks. Think of them as flexible function approximators. They can take any input and produce any output, whether that's predicting stock prices from market data or classifying images into different categories. The key insight is that neural networks are incredibly flexible for any input to output mapping, provided you have the right representation. But language presents a unique challenge. How do we represent words as numbers that a computer can understand? We could use ASCII encoding, where each character gets an arbitrary number, but this has no semantic meaning. Or we could use one-hot encoding for words, but again, this is arbitrary. The words dog and cat would have no meaningful relationship in this representation. This is where the vast field of representation learning comes in. Essentially, we can teach computers to learn meaningful word representations through one clever type of model called autoencoders. We make a neural network compress high-dimensional, arbitrarily assigned word vectors, like those from one-hot encoding, into smaller, more efficient representations, and then try to reconstruct the original. The magic happens when the neural network is forced to learn efficient representations of the data, so it can accurately reconstruct the original. These efficient representations are called embeddings, and they're the backbone of modern language models. The vector space these embeddings live in is called the latent space, and values here actually conveys semantic meaning. Here we get the answer to our question of how we can perform operations on words. We can do vector operations. This is how we get the famous result that king minus man plus woman equals queen. This is good progress, but we still have a problem: context. A word's meanings change with context. For example, the word mole can mean a spy, a unit of measurement, an animal, or a mark on someone's face. In our current representation, all these meanings would have the same vector representation, but they clearly mean different things depending on the words around them. We need a way for words to understand their context. This is where the concept of attention comes in. Each word can pay attention to every other word in the sentence to understand its context. The amount of attention that each word pays to each other word is how much context it gains from it.
Here's how it works. Each word generates 3 vectors from itself. A query vector, effectively representing the question, what should I pay attention to? A key vector, representing how a word should answer a query. And a value vector, representing the actual context to be shared. The similarity between pairwise query and key determines how much attention each token has to pay to each other token. Then, the target token's value vector is scaled by that attention amount and added to the original word vector to actually pass along that context. How are these query, key, and value vectors determined? You guessed it, more layers in a neural network. Everything is just modeled with learnable parameters. Mathematically, this becomes the famous attention equation, which packages that idea into a nice matrix multiplication, where our similarity metric is just an inner product, allowing us to use more optimized algorithms for these calculations. The softmax ensures the attention weights sum to 1, and the scaling factor prevents the dot products from growing too large. This creates contextualized representations where each word understands its role in the sentence by getting shifted by each other word by the right amount.
Put it all together and you have a transformer. Inside language models, you'll see multiple attention heads running in parallel, each learning different aspects of language, like syntax, semantics, and relationships. Then, with all this context, the model predicts what the next word in the sequence will be, ultimately generating coherent, meaningful text. It's kind of crazy how this is all just effectively autocomplete, but it's the context that self-attention provides that makes it actually work. In practice, a lot of what I explained is handled slightly differently, like embeddings generation and positional encoding, but the core idea is the same. Thank you all for watching, and I hope you found this video insightful. Check out the blog post for a much more detailed explanation of the same topic. After all, this was generated from that. Like and subscribe and follow me on X for more updates.